Welcome to the next seminar in the non-commutative geometry series. So this week speaking is Daniel Gromada from Prague, from the Czech Technical University, and he will speak about diagrammatic categories and free quantum D4+. Okay,
thank you. And first of all, let me say hello to everybody and nice to meet you, since I was looking forward to meet with you since I'm in Prague, beginning of this year. Unfortunately, it was not possible to do in person, but at least I'm glad to have this talk here. So I will talk about diagrammatic categories and quantum groups, which is also kind of basically the topic of my PhD thesis that I did in Saarbrücken in Germany. And so this, in the first part of my talk, I will do some general introduction to this and show how categories and quantum groups are connected together and how we can apply this theory to quantum groups. And then I will show some specific application, namely I'm going to define some free quantum analog of Coxeter group of type D with this rank equals to 4, which is the content of this archive preprint here. Okay, so the first part, compact matrix quantum groups and diagrammatic categories. So I guess most of you know what are quantum groups. I'm in particular working with those compact matrix quantum groups, but anyway, I put here this brief definition just to recall it. For me, a compact matrix quantum group is a pair of a C-star algebra A and some matrix with entries in this C-star algebra, such that those entries generate the whole C-star algebra. The matrix itself and its transpose is invertible, and we have this star homomorphism, which is of course the co-multiplication. So yeah, I find this particular definition quite nice because I find it slightly more maybe easy to understand than the Hopf algebra approach. Also a nice thing is that actually, if we assume here not only U and U transpose to be invertible, but also similar to some unitary matrix, and instead of C-star algebra, we could also work with star algebra, and the compactness or the C-star structure will then be somehow automatic. So this is what I work with. But anyway, if somebody doesn't know about quantum groups, the best way how to learn it is maybe through some examples. So this will be the typical example that I will consider. So we may start with an orthogonal group. So that's a group of orthogonal matrices, right? So matrices that have real entries and they are orthogonal. And we can also describe this as a quantum group. So the C-star algebra here, the meaning will always be the continuous function over the group or the quantum group somehow. And this can be, in this case, described as the universal C-star algebra generated by some elements Uij that satisfy some relations, and those relations exactly copy those here. So this self-adjoint entries, this corresponds to this. This is the orthogonality of the matrix. And in addition, we of course have to say that the C-star algebra is commutative, because functions commute. And now the whole idea of quantum groups is that we can somehow drop or deform the commutativity. So I usually work with those quantum groups that are made by somehow liberation instead of deformation of those commutation relations. So I typically want to get rid of this commutation relation completely. So if I take the same set of relations, but removing this commutativity, I can define the so-called free orthogonal quantum group, which I denote by Orn+. Okay, so that's the typical example. This was defined by Wang in 1995, and there are several other similar examples. For example, the free unitary quantum group, just the kind of the universal quantum group, such that this fundamental representation U is unitary. Or the free symmetric quantum group, where we have those relations. So those UIJs are not only self-adjoint, but also projections, and they sum up to 1 per row and per every column. If you think about it, if those UIJs were numbers, this exactly means that all of them are zeros or ones, and this means that there is exactly one per row and column. So those are exactly the permutation matrices.
Daniel, can I stop you 1 second? Just the invertibility of U and UT, how does that relate to the antipode on the dense? This is a strange way of looking at things for me.
Yeah, so that's maybe also good to point out that in this definition you don't have to assume the co-unit and antipode. It somehow automatically follow from those axioms. So it, well, things are more simple if you, for example, assume that this U is unitary, and then the antipode goes map like from oh, now I'm a bit confused, like from UIJ to UJI, right?
Mm-hmm.
Yes.
So it should give the inverse matrix somehow, but I guess the invertible, then the matrix that's going to invert U should.
Yes, sorry, yeah, exactly. That's the inverse. Yes.
Yeah.
But yeah.
Okay, you don't need it, is what you're saying, and it's all encoded inside of this.
No, not really. Yeah. But of course, you should then show that this extends to the whole algebra, but actually, just giving those axioms, you can already build the representation theory, and then you have the thing that the algebra is generated by the entries of all irreducibles, and then you have already the basis, and you can define the antipode explicitly. Well, anyway. So and as you can see here, what's important here are those relations. So those relations kind of define the quantum group. So we would like to encode the relation somehow, and we are going to do it using some diagrams. So some of those diagrams I've drawn here, and I guess some of them are intuitively understandable. For example, this is the commutativity. So you take UIJ, UKL, and you can commute them. This is another diagram that is kind of intuitive, I guess, and that's some kind of relaxed commutativity. So the relations goes like this. You can swap the entries according to the diagram. Those are maybe not really clear how this corresponds to each other. So this single point, that's some one-dimensional subrepresentation, and this, for example, means that this S equals to 1. Well, anyway, I will explain the relation more formally later. But again, this one is maybe more intuitive. Again, we have this one-dimensional subrepresentation S, and this has to commute with everything. So this is the relation. Okay, so now I will explain more in detail how this works, and the idea is somehow inside this diagram. So we have this compact matrix quantum group, and inside we have some relations. And in addition, we will consider those intertwiners or intertwiner spaces. So how this works. So if we start with the quantum group, then what are the relations? That's clear, I guess. Those are, let's say, all polynomials that evaluate to 0 if you put the generators of the algebra. What are the intertwiners? Those are exactly the intertwiners from the representation theory. So if you have some representations U and V, you can consider the intertwiner between them, so the intertwining operator. And if we in particular consider those matrix quantum groups, then actually it is enough to consider not all representations, but only the tensor powers of the fundamental representation. So here I consider intertwiners between u tensor power k and u tensor power l. So this is some linear operator t that commute in this manner. So we define the intertwiner spaces like this. I should point out at this point that here I somehow silently assume that all the entries of this U are self-adjoint. So this I will assume in the whole talk. If this was not the case, so if we weren't in the, let's say, orthogonal case, but the unitary one rather, then this would be slightly more complicated because you would have to somehow also describe how those URG star work. So here you would have to have more representations slightly, but it would also be possible. Okay, so those are the intertwined spaces, and the important point is that they form a category. What this means is that, okay, if I have intertwiner from u tensor power k to u tensor power l, and then from L to M, I can compose them, and that's an intertwiner from K to M. So there's a category structure. And now, so this is going from here to here. And now I want to reverse also those arrows. So, and that's using this Coronovich Tanaka crime duality, which says that I can take any rigid monoidal star category that has the morphism spaces realized by such linear operators, such that they would fit here. Then there exists unique, in some sense, unique compact matrix quantum group G, such that this is exactly the representation category. So the category of the intertwiners associated to the quantum group. I will, of course, not prove this theorem, but one way to prove this is exactly going through those relations. So if some T has to be an intertwiner, then this by definition means that this equality holds, and I can consider this equality, and I can treat this as some relations that I want to impose in my algebra. So I take, let's say, the ijth entry or jith entry of the left and right hand side and write it as a relation. And actually, it's just enough to take the linear span of those relations, and I automatically obtain an ideal or a bi-ideal that I can quotient out from the free algebra, and I obtain some algebra. And what's slightly more complicated to prove is that this algebra indeed defines a compact matrix quantum group. So this is how it works. So for me, intertwiners are somehow indexing relations or something like in this sense. So intertwiners are for me the basis, the application of intertwiners are for me that they determine relations of the quantum group. And now what I want to do is I want to model those intertwiners using those diagrams.
Sorry, there's a question in the chat. They're asking, are these representations of the compact matrix quantum groups co-modules over the Hopfeld?
Yes, okay, so maybe I should have made this clear what the representation is. Yes, so this is a co-representations of the associated algebra or the Hopf algebra. Yes. So in particular this U, so that's a matrix with entries in the algebra. So that's a co-representation of the algebra. And this is an example of representation of my quantum group. And of course, its tensor powers are also representations or co-representations, or how you want to call it. Right.
Okay, thank you.
And so one idea how to do this, or one idea, well, so as I said, I want to do this using those diagrams. And one example, classical one kind of, is the so-called Brouwer category, Brouwer diagrams, which are pairings of some set of points on some upper line and some set of points on lower line. So here I have 4 points here and 6 points here, and now I pair them together. So those strings denote this pairing. And yes, so I can define this set of all pairings of k upper and lower points. And now I want to give some interpretation to those diagrams, and I do it as follows. So those vertical lines here, I mean, starting with this diagram. Sorry, I can draw here. Starting with the diagram, I can put here at this point a copy of some vector space V, where V is some c to the power, like Cn. So here are copies of some vector space, and those straight lines from top to bottom, those are just identities from V to V. Right. So there's this. Now I have also some of the pairings like this. So this can be any bilinear map. So I can take, for instance, this canonical one. So just delta ij, and those pairings on the lower rows. This will be should be some bivector, let's say. So this will be kind of the dual of this form. So here it will be the sum of ek tensor ek over all k's, where this ek is some basis. So in this sense, this is just a map from 4th tensor power of V to 6th tensor power of V, and so it stands for some linear operator, which we can interpret as an intertwiner. And actually what this Brauer duality says is that if I take all the maps TP associated to those pairings with k upper and L lower points, then those are exactly the intertwiner spaces for the orthogonal group. And so now let me go back to this diagram. So I can start with orthogonal group, and I claim that those are the intertwiners for the orthogonal group. But I can go also the other direction, thanks to the Coronovich Tanaka grind, or this is the classical version, so just Tanaka grind maybe, and which says that I can start with this power category, interpret it like this, and now this means that this defines some group or quantum group, and this quantum group is exactly defined by relations like this. So this means that orthogonal group can be described as a quantum group where, okay, this is my assumption that all those uij's are self-adjoint, and in addition, in the algebra, I have all those relations coming from the intertwiners. Okay, so that's the reverse direction. Right. I will get back to this again in a minute. But before that, I want also to point out that those diagrams also allow us to model the category operations. So if I have two pairings like this, I can compute the tensor product using those diagrams just by putting the diagrams side by side. I guess you can believe me that it works like this. And yeah, so if I put the diagrams side by side, so I kind of make the tensor product of the diagrams, then this corresponds to the tensor product of the associated linear maps. And also for the composition here, I put the one diagram below the other one, right? So if this is identity from V to V, and here I have identity, then if I compose them, then I somehow have identity from here to here. And also the pairings must be somehow well chosen such that this works. This is also the identity, so everything works here. Involution is just flipping with respect to the horizontal axis. So it works like this. So I can model the category using the diagrams. Okay, and now let me recall what I just said on the slide before, that the orthogonal group, thanks to the Brauer duality, can be described using those intertwiner relations like this. So I take all the pairings, all the possible pairings that I can think of, and put them as a relation in my C-star algebra. But actually, thanks to the fact that I can also study the category operations, then I can ask, what is the category generated by? In the sense, well, I claim that this category of all pairings is generated by this simpler pairing and this crossing. What I mean by this is, maybe let's go back here. I have this, okay, I have this example here, and I claim that if I start with the normal pairing and the crossing, and of course, by definition, I assume that there is also the identity, and here the identity is just the simple string like this. I can really construct everything using those operations. And really, if I start with this, I can put here, like, I have those two through strings like this. I can put them here. I can put those two pairings here that I will need. I can put the pairing here. So this is what I can construct from just this pairing and this identity. Well, I recall that if I take the adjoint of this pairing, I get this one. So this is why I can do this here. And now I can use this crossing to commute some of the points here, like put it here and put it here, and do the composition, maybe some identities here, and this is then exactly this P here. So this is a kind of a proof that every pairing is generated by those elements, and somehow those operations on the pairings exactly, or the operations in the category exactly corresponds to the manipulations that I can do with the relations. So in particular, this means that if those two pairings generate the category, then the associated relations have to generate the ideal that define the algebra. So actually here, if I define the associated algebra, I can only consider the relation corresponding to this pairing and this crossing pairing. And if I look what exactly those relations are, if I use the definition and write this down, then you will find out that this one is exactly the orthogonality, and this one, this I already said, that this one is exactly the commutativity. So here I obtain exactly the same definition as I had here. Okay, so that's how I can kind of reconstruct this group from the representation category using the diagrams. And now an idea might be consider some other category, diagrammatic. For instance, this temporal leap category. This is the category of all non-crossing pairings. So this is, for instance, non-crossing pairing because there no strings are crossing each other. All the other examples here, here's a crossing, here's a crossing, here's a crossing. Also here is crossing. So those we don't want to consider, but this one is okay. And this one is generated by the single pairing. Simple argument is before can be applied. Okay, so what is also important is that this is actually a category, because if I take just the non-crossing pairing and apply the category operations, then I can also only construct just non-crossing ones. So that's fine, that's closed under the operations. And we can ask what this category corresponds to. And it is exactly the free orthogonal quantum group, because I can again write down just the relations corresponding to generators, and that's what I'm left with, just the orthogonality, and I'm missing now the commutativity here. And that's somehow a general idea. So that's the maybe the point of what I want to say with my talk here, is that we can construct those free quantum groups, so quantum groups where we don't want any commutativity, by exactly this procedure. So if we describe the representation category using some diagrams, then typically the diagrams involving some crossings correspond to relations that involve some commutation. And if we remove all the crossings, then we remove all relations that correspond to some commutation, and we end up with some free quantum group. So that's one possible construction here. I'm going to give you another example, which is using the category of partitions. So instead of pairings, we may use partitions. So instead of decomposing the upper and lower point into pairs, we just decompose them into any subsets. For instance, here there's 3 upper points, 4 lower points. So those points, all of them are in one subset, and there are 2 singletons here. Here 3 singletons, and here this is one subset, and here this is one subset. And again, I can give here some interpretation. I'm not sure if it is clear what I meant with this notation here, but the idea is that I use somehow blockwise Kronecker delta. So maybe if I start with this partition here, then what will be the associated intertwiner? I can put here some indices. I'm not sure if I'm able to write this such that you can read it, but here I have I1, I2, I3, I4. Here's J1, J2, J3, J4. And here, this is somehow TP or TQJI, and this will be delta, and I go over the blocks. So here, this block has I2, J3, J4. So this is delta, I2, J3, J4. And the other block is delta, I3, J2. So you can see that it really extends the definition before, because this block is a pairing of 2 points, and it really corresponds to an identity going from here to here, because here I have this Kronecker delta here. So that's identity. Right. And the claim is that this category with this particular interpretation corresponds to the symmetric group represented by permutation matrices. Okay, that goes back to Jones, and we can do the same trick, and this trick of removing all crossings that actually was introduced in this article of Theo Banneker and Roland Speicher, and they describe this example of this free symmetric quantum group corresponding to the non-crossing partitions. So again, here you can consider non-crossing versions, and that's exactly it. And again, what's important here is that we can model the category operations exactly the same way as before, tensor product, putting side by side, composition, putting one below another, involution by reflection. And maybe one detail that I did not mention last time, but it also applies to the pairing situation. It can happen that some block here will not be connected to any of the new upper and lower points. If you do the composition here, so I have some 2 blocks that are kind of empty, and if I want to keep this mapping to be a functor, then I have to replace each of those empty blocks by this scalar factor n here. So it's kind of a detail. So actually, I should consider some linear structure over those partitions to make this work. So right. I could also work in general with linear combinations of partitions, which would just be kind of complicated, but it would also work. So that's it. And finally, I just want to give some summary and give some references to this theory. So probably this is not complete, but that's some stuff that I'm interested in. So what you can do with this? First of all, you can extend the partition category even more. So for instance, I said that all this applies just to the orthogonal case because we did not somehow handle those adjoints, those Uij stars. So if you want to do that, you have to use colors. So this is what was introduced in this article of Pierre Tarragon and Moritz Weber, and also Marie Frelon was working on it. And you can also do some other, use those colorings of those points to describe some other stuff. But for instance, if more than just one representation is somehow important, so until here we had just one fundamental representation. If you have more, then maybe you want to use more colors. So yeah, I also did some stuff here. You can also add more morphisms. So we went from pairings to all partitions. And for instance, in this article of Laura Manchinska and David Robertson, they use the category of all graphs. So this is even larger category with the same, so more morphisms and the same set of objects. What you can also do is kind of make the braiding non-symmetric. So if you are interested in those deformed quantum groups, deformed commutativity, then often those representation categories have non-symmetric braidings. So you have to distinguish between kind of the braiding and its inverse. And then I guess you know those diagrams from those Young-Baxter equations and stuff. I have to say I don't work with this at all, so I'm not an expert for this, and it's also why I don't list here any references, although here should be probably some very long list here, but yeah, I don't know very much about this, so that's it. So that's about this, and also what you can do is to study some subcategories. So this is
to interrupt. Just
yes.
then, so for all of the examples that you did before, for all of the orthogonal, free, and so on, the braiding is always symmetric.
Yes, well, in the sense, if you consider the groups, and then what I did was to remove those crossings to consider quantum groups, and there you don't have the braiding at all because yeah, you don't have any commutativity.
Thank you.
You can also study subcategories, and this is convenient because any category of partitions, let's say, or any category of pairings, you can use the same functor, and you have to, using the Tanaka Klein duality, you obtain some quantum groups. So you have new examples of quantum groups just by looking for examples of those partition categories. And the classification is actually done in the so-called easy case. So this means that you are considering just the partitions and not their linear combinations. This was a series of articles of Sven Raum and Moritz Weber. So this is done, but you can still have fun with this if you consider some of those generalizations. So for example, those two-colored case describing this unitary quantum groups, this is somehow work in progress. I have some result here, some results where obtained already in the original article here, and a lot of results are now were obtained by another PhD students of Moritz Alexander Mank. So there's this. And finally, what you can also do is looking for non-easy examples. So working with those linear combinations where I obtained some examples, and also Laura Maassen obtained some examples. So we have examples in this case, but as I said, this case is not very nice, and maybe more convenient is if you have some quantum groups that cannot be described by just partitions. Maybe you should look for some other combinatory description, which is more convenient. You can also modify the functor interpreting the partitions or the diagrams. So for instance, you can reinterpret this pairing, and you can get, if you consider this category of all non-crossing pairings, you get those so-called universal orthogonal quantum groups, or with colorings, universal unitary quantum groups. If you but this does not work with those crossings. This would be, I guess, more complicated then. You can also keep the interpretation of the pairing, but somehow twist the interpretation of the crossing. So if you consider the Q equals -1 deformation of the orthogonal group, then this quantum group actually has a symmetric braiding. So you can describe this by the theory that I described. Yes, so it works like this. So you can take the category of all pairings, and if you twist this crossing, then you get the ON deformation at Q equals -1. And finally, since all of this describes somehow the representations, you can study the representation theory, for example, study those fusion rules and stuff. The partitions can be helpful also for this. Right, so this was some summary of some interesting results, and now I would like to go to this one particular result I wanted to present to you, and that's this free quantum analog of this Coxeter group D4. Yeah, so, or maybe if there are some questions now, you can ask, but if not, then I will continue. So what is a Coxeter group of type D? So maybe why is this question interesting? The point is that there are those Coxeter series, those Coxeter groups, and we have this series A, which is the symmetric group, and we have a free analog for this. This is the free quantum symmetric group. The series B and C, this is the hyperoctahedral group, and for this we also have the free analog. And then there is this series D, for which we don't have any analog. So that's an interesting question, whether there is some free analog of Coxeter groups of type D. And what actually is this Coxeter group of type D? One possible viewpoint, okay, is maybe through those symmetries. Yes, sorry. Yeah, I wanted to start with this hyperoctahedral group. Sorry. So what is a hyperoctahedral group?
Sorry, Daniel.
Yes.
I have a question. I don't understand when you say dihedral is different than the other. It seems to me that it is the same. I mean, why do you say it doesn't have a realization? I didn't understand the remark. When you said for D, there is no free realization, a phrase like that you said. I'm just confused.
Yeah, first of all, by type D, I mean really this type D in those Coxeter diagrams. So that's not the dihedral.
Oh, okay, fine.
And if I say free quantum group, I don't mean free in the group sense, but
oh, okay. sorry. I understand. Thank you. In that sense, you used before. Okay, thank you. Sorry.
Okay, and okay, so I wanted to start with this hyperoctahedral group. So what is this? This is, you can view this as a symmetry of the n-dimensional hypercube or symmetry of n copies of a segment. And you can also realize this using matrices. So this is the group of signed permutation matrices. So I take a permutation matrix and put some minuses in front of some ones. And now the Coxeter group of type D is the index 2 subgroup. So we have to assume that n is at least 4. And then we can consider the index 2 subgroup given by the relation that if you multiply all the signs, that you have to have 1. One way how to write this down somehow is to say that the permanent of this matrix is equal to 1. What is a permanent? Permanent is almost like determinant, but we are missing here the sign here in front. And so you may ask why this is even a subgroup, and because and this is quite an interesting point. At least I find this interesting. That although so the permanent, there's a notion that exists in the theory of matrices, but it's not as important as determinant because it's not multiplicative. It is not a representation of general linear group, for instance. So why this is a subgroup? Well, this has an interesting quantum group interpretation. The permanent actually is the same thing as the Q deformation of determinant for Q equals -1. And if you look at those matrices, so at this hyperoctahedral group, then this is actually not only a group, but it is also kind of a anti-commutative quantum group. So because since at each row and at each column you have just one non-zero entry, then it means that those entries in the rows and columns not only commute, but also anti-commute. So not only the determinant, but also the -1 determinant is a representation of this group. Okay, so that's the reason why this is a subgroup, and yeah, that's what we want to work with. Now, so as I said, the idea is describe this group using partitions and then kick out all the crossings. So the hyperoctahedral group that is a partition quantum group, and this corresponds to the category of all partitions with blocks of even size. So that just means that all the blocks here have an even number of strings going from them, and this is actually generated by those two elements, the crossing, of course, and now this 4 partition. And if you write down exactly the relations corresponding to those two partitions, then except for this self-adjointness, you get the commutativity, of course, for the crossing, and this relation for the 4 block. Yeah, and if you think about it, then exactly, yeah. So, okay, sorry. I guess here is a slight mistake, or so now what I didn't say is that now if I say generated, then since I'm lazy, then I always assume that the pair partition is also inside, because I somehow want my categories to be rigid categories, and this pairing is somehow duality morphism, but I have to put this relation inside here. So here I must also assume this orthogonality. So sorry, this is missing here. So like this. Right. And if you write this down, this relation, actually, if you think about it, just means that at each row and each column, there's just one non-zero entry. And since the orthogonality, this non-zero entry has to be just 1 or -1. So this is really the hyperoctahedral group. So Now you can believe me this, I guess. And now what we want to do is to do this subgroup with respect to the permanent being equal to 1. So now we do the dual thing. We work with those algebras. So now we need to go to the quotient algebra, factoring out this relation permanent equals to 1. And since, as I said, the permanent is a representation, you can probably believe me that this is intertwiner-like relation. So more concretely, this relation can be written as follows. This P, this is an element of nth tensor power of the vector space, and it's exactly the invariant, the generator of the invariant subspace corresponding to the permanent as a representation. So you can write down this P in its entries, P I1 up to In equals 1, if this I1 to In is a permutation of the numbers from 1 to n. So if two those indices coincide, then it is 0, and if those are mutually different, then it's 1. So this is, and this relation exactly corresponds to this permanent equals 1. So what we can do is take this category and to add this P to the generators here. And so let's assume now that n equals to 4, and we can actually describe also this permanent or this tensor P as a partition thing. And we can do it as follows. So this is something. So I'll just briefly explain why this is true. So those are 4 singletons. So the associated tensor would be just 1 for any at all entries. There would be just 1. But what we actually want is that if the first 2 indices are the same, then it is 0. So we subtract this partition, which is 1 if the first 2 are 0. And we also subtract this one and this one and this one and so on. But we subtract it now too much because it can happen that also the first 3 are the same, and we subtracted this kind of twice or 3 times actually. So we have to add something and subtract and add and so on. So, well, now as I look at it, I'm not sure if now here shouldn't be minus. Well, anyway, it works somehow like this. And you can do this also for any n, but then the size of the partition would be larger, but it would work like this. So, okay, so this can be here. And now, what you can do is to interpret this Dn as a partition quantum group where this is partition, and this is also partition. And now the idea is to kick out all the crossings. So you could remove this simple crossing and leave those 2 there. But the point is that in this P inside, here is this summand here, and here this is also a crossing partition. And therefore, you should not call the resulting quantum group free because you still have some crossing inside. But a trick that we can do, and unfortunately, or I don't know if unfortunately, but that's how it is, we can do this only for n equals to 4. We can subtract this crossing from this P, and suddenly, of course, we obtain a non-crossing partition. And so we can define the new quantum group, which we call D4+, to be the quantum group corresponding to this category. So this is my definition of D4+, and that's it. So let me again stress 2 things that make this definition interesting. First of all, the associated category is non-crossing. So it's good to call this quantum group free. And secondly, if you add this crossing back to the category, then this crossing, this partition that we subtracted, there's just rotation of this crossing. So actually you can rotate partitions inside the category, which I did not say, but that's how it is. That's how it is. And therefore, if you add back this crossing here, then you can kind of somehow remove this change here, and you obtain back this category here. So adding the crossing back to the category, you obtain again the D4. And this means
there's a question in the chat. What happens for n is greater than 4?
Yeah, okay. Okay, so I just finished this. So this means that I can call this the free version of D4 So, or I can say that D4 is a classical version of this quantum group, because imposing, in addition, the commutativity to the algebra, then we can we recover this D4. What happens for n equals 5, let's say, is that here I would have not just one crossing partition, but more crossing partitions, and not only such simple crossing as this, but I would have here maybe something like, I don't know, something like this, for instance. And this means that if I subtracted those crossing from the P, then I would obtain some other quantum group. So if I subtract those crossings and remove this crossing, and then if I wanted to go back and add the crossing back, then I'm not sure if I could somehow generate those things to put them back somehow. So then if I did the same thing, then I could not say that the classical version of the new quantum group is D5 or Dn, because it probably would not be like this. So that's the point. Yeah. I'm not sure if it's understandable, but
so the comment back is, okay, so the point is that by removing them, you may lose information. Is this it?
Yeah, so yeah, the point is that by okay, maybe I should have written it here. So I can, let's first of all do nothing and write this down. This equals to crossing. Now I have the 4 partition, and now I have P minus crossing. And the important point here, that here I have this equality here, and now I can say, let's remove this crossing now, and then everything is already non-crossing, and I have a free version of my quantum group. But I cannot do such a thing for large n, because then I could not just subtract the crossing from P without changing the category.
Okay, thank you.
Okay, so I guess this is maybe already interesting for itself, and some questions arise now, which are open questions. So everybody's invited to think about them. First of all, is D4 plus a member of some larger family? Are the n plus for n larger than 4? Okay, so that's exactly this question that was asked here. I cannot do the same thing as I did now, but it still can happen that there are some dn pluses for larger n. Is D4 plus a reasonable analog of D4? Yeah, so there's maybe some ill-defined question, but what I mean by this, for instance, is D4 plus a quantum symmetry of something? So that does it appear naturally somewhere where classically the D4 appears? So those are the questions. Yeah. So what I also wanted to say and didn't is that this construction is kind of strange in the sense that here, if classically, it's kind of a usual thing of taking some group and taking a quantum group, or it's, I guess, even normal quantum, taking a subgroup corresponding, defined by some subrepresentation, saying that some representation equals to 1. But this is not what we are doing in the quantum case, because this is impossible to do in the free case, because there's no free version of determinant. If you take the free hyperoctahedral group, it has no one-dimensional representation. So we are not doing the classical thing here. We are just so it can happen that this exists just by some coincidence, but it is not a member of some larger family, because this D4 plus actually does not have any clever sense or something. But on the other hand, as I said, that this Hn, for example, is the hyperoctahedral group, that it's a symmetry of n-dimensional hypercube. Then if you do this quantum, then you obtain here something that you would not expect, namely that the quantum symmetry of n-dimensional hypercube is not free Hn plus. It's not also not the classical Hn, but it's the Q equals -1 deformation of orthogonal group, because if you impose commutativity to this anti-commutative orthogonal group, then you get the hyperoctahedral group, which is kind of strange, but that's how it is. So the thing that we did not construct it the classical way does not mean that it does not have this classical, so the same meaning. So it really is an open question whether this works. Okay, so, and this is my last thing. I would like to model the representation category of this D4 plus, because although I defined this D4 plus using the partitions, so I kind of know the representation category. I actually know just the generators. I have no idea what are the elements of this category. So I would like to find this out. And how do I do this? So first of all, so I start with okay. So this is my for block. As I said, I can rotate my partition. So this is actually it's the same generator as if I drew it like this. So that's fine. And then I define this kind of white for block. I define it like this. And if you notice here, then it is almost the same thing as this P minus this crossing here, with the change that I'm putting twice the for block here, but the for block is anyway in the category. I'm subtracting these two pairings, but those are also anyway in the category. So actually this thing equals to my category here. So this is kind of more convenient set of generators. And why it is more convenient? That's because it actually holds that this white for block generates a category that is isomorphic to the category generated by this black for block, by the normal for block. So what this in particular means that since sorry, I would like to draw here. Good. Since here I have not only this for block, but all, as I said, all blocks of even size. For example, I have this block like this and all the other blocks. I can define, okay, not only those are isomorphic, but the isomorphism maps this black for block to the white for block. So I can, applying the isomorphism, I can define also white 8 block, for instance, and so on. So that's what I can do. And actually, so if I study this category, that what are elements of this category? Those are I can just take those black blocks and white blocks and somehow connect them together, and yeah, this will be, I obtain elements that look like this maybe. So this just says me how to compose those two generators together, like contract those two and so on. So what I obtain is, I obtain essentially some graphs. So those black and white points are my vertices, and in addition, well, those are not only graphs, but I have also those input-output strings that, yeah, some more special graphs or more. Well, anyway, those are again some diagrams. Okay, so what exactly graphs are those? So first of all, those are planar graphs, because I have here non-crossing generators. So I can just generate non-crossing diagrams. Okay, that's okay. Those are bipartite. So why I can also only consider bipartite graphs? Well, if I had two black vertices neighboring each other and maybe some strings here, then actually using this definition of composition, I can contract this edge and put just one vertex here that have all those strings going out of it. And since those black and white vertices are isomorphic, I can do the same thing for the white vertices. All the vertices have even degree. That's because I use those even degree generators. And there are no vertices of degree 2. Why is that so? If I had some vertex of degree 2, either black or white, I can actually say that this equals to just a simple string. So I can remove all vertices of degree 2. There are no multiple edges. This is actually the most interesting thing. If I take a black point and a white point and connect them with a double edge, and here again there might be some strings going out from here, then you plug in here the definition of the black and the white point and use the partition calculus to compute this, and you find out that you can actually, that this equals to the same thing if you remove the double edge. The only thing is that you should probably, you should put here a factor 1/4, but that's not so important. So you can forget about this factor if you are only interested in the combinatorics. So that's a good point, but we don't have to consider multiple edges. And there are also no isolated vertices. This is the thing that I was talking about, that if I have isolated vertex, then this actually equals to n. And here we have n equals to 4. And that's the same for the white point. So I can consider a category filled by those graphs as a new diagrammatic description of my new quantum group. And yeah, I guess I should end in a minute. And now I listed here as a theorem because it's really an important point that if you consider all those graphs and you fix the number of input-output vertices, then there's a finite amount of such diagrams. And this is important because this only allows me to really compute something, to really in finite amount of steps compute what actually explicitly are the intertwiner spaces. Okay, and this is, I think, an interesting category actually. So you can study just the category and ask some questions like, is the functor interpreting those graphs injective? So are there some other reduction rules, or is this everything? Also a question, are there some other fiber functors? So is there some other interesting interpretation using some other functor here? How many graphs are there actually? So as I said, I know that there's finite amount, but I actually don't know how many. So this is also an interesting combinatoric question. So those are some open questions again, and well, that's it for my presentation. So thank you for your attention.
Thank you very much for a very nice talk. So we start, there was a question that we didn't get a chance to, the question in the chat, so I'll start off with this from Ruben. So he's asking, the crossings appearing for n greater than 4, can you describe them in terms of elementary crossings and non-crossing so that you can only remove the elementary crossings? This is written in the chat if you want to see it written down.
Yeah, okay. So the point is that for n equals to 5, I would have partitions on 5 points. So those will not be elementary crossings, and since those are 5 points, this will not be a pairing. So it will definitely not be generated by the simple crossing, because the simple crossing is pairing, so it only generates pairings. And in the n equals 5, yeah, there are no pairings, so it cannot be generated like this. Right.
Okay, good. So are there any other questions from the audience? We've had quite a few so far. Yeah, so if not, I probably have a question. So are these compact quantum groups, all of the ones, the free, orthogonal, so on and so on, are they of Katz's type?
Yeah, good question. So those that I was talking about are of Katz's types, but for instance, there are those free, so this, for example, this ON plus, this is of Katz's type, and yeah, I usually work with subgroups, quantum subgroups of this one, but there are also those universal orthogonal quantum groups, this O plus F. So this means that let's say also the unitary, maybe the unitary are either one. So the universal unitary free quantum group, this is this U plus F, which means that the fundamental representation is unitary, but the transpose is not. This is just similar to unitary, and the similarity matrix is this F, and this is not of Katz's type. So this one you can also describe using those pairings, but then if you wanted to study some quantum subgroups of this one, this I think would be slightly complicated.
Okay, thank you. And then a last question, well, we check, are there any more questions?
I had one non-mathematical question.
Yeah.
I just like the way your slides are set out with the border of the theorems and the propositions and things. And then what was the style file or whatever that you're using for that?
So this I made by myself, so that's a style file.
No, okay, no, it's very cute, very nice.
Yeah.
So can I ask a question then? Do these guys, I mean, they admit maximal tori, I guess. I mean, you're going to have a projection from the quantum group, the free quantum group, onto commutative tors.
Yes. So those, yeah, again, I typically, so if you use the orthogonal one, then that's typically Zn, Z2 to the power of n, or something like that, or that's, yeah, actually not many possibilities, yeah, for the partition ones.
Yeah. The thing is that if you have a maximal torus, though, then you can look at the invariance of these things, and then you get flag manifolds, quantum flag manifolds of these quantum groups, which is something I would be interested in. But that's more of a comment than a question, really.
Okay, yeah, that's interesting, yeah.
Okay, so are there any other questions? So last chance. No, I guess we had quite a few during the talk. So then we thank you again for a very nice talk. And now it's time to announce next week's talk. We can get it on the screen. The technical department is taking care of this. Yep, so next week it's going to be a double header again. So it's Zahra Hasnapour Yakdani from the Nasir Tushi University of Technology in Iran, and Ali Rad from the University of Glasgow. So the first talk will be about frameless Hilbert C-star modules, and the second talk will be about the existence and uniqueness of inductive limit Cartan subalgebras in inductive limit C-star modules. So hopefully we'll see you all again next week. Thank you for coming. And that's it.